And we can move on with our session to our next speaker, who is Qianxiao Li. It's my great pleasure to have him here. He's an assistant professor in the math department at National University of Singapore. He graduated actually with a BA in math from the University of Cambridge, so it's almost like a homecoming for him. And then he got his PhD in Princeton. And his research interests include especially the interplay of machine learning and dynamical systems, stochastic gradient algorithms, and many related things. So today he's going to talk about approximation theory for machine learning for and with dynamical systems, my guess would be. So with that, take it away, Qianxiao.
All right, thank you, Lars, for the nice introduction and for inviting me to give a talk at this conference. It's very nice to give a talk here. Of course, it would be better if we can visit CMS again. So today I'm going to talk about some recent work I've done with my collaborators on the interplay of machine learning and dynamical systems. Now, I'll focus most of my talk on approximation theory, but as you can see, for example, from the first talk by Rama today, that this connection actually goes way beyond approximation theory into generalization and optimization. So today I'll mostly be talking about approximation. So to describe first some ways to roughly classify these connections, one observation I just want to make is that if you think about it, a lot of this modern innovations in deep learning really has a dynamical flavor to it. This, you can think of it as coming from roughly three categories. The first one is the models, right? So we have a deep neural network model where it is stacking many layers of this shallow neural network layers together. And through composition, you can think of it as some discrete form of dynamics. And of course, you can take the continuum limit of that. You arrive from an input to an output. And through this composition or dynamics, you can build complexity. Of course, in the recurrent network arena, this is even more pronounced, where you basically iterate the recurrent neural network over and over again, theoretically indefinitely, to produce a sequence. So on these models, there's a lot of compositional and dynamical structures. Now, in the data as well, we're seeing a lot of applications of deep learning to scientific problems involving time series. So we are starting to go beyond, let's say, natural language processing and video analysis into probably using deep learning or machine learning to resolve some scientific problems involving computational chemistry, etc. And you see a very interesting interaction of this deep or dynamical structures in the model, as well as this data, which are also dynamical in nature, right? So this poses a lot of interesting mathematical questions and how they interact. And finally, when you think about learning, there's usually some training algorithm, and the prevalent algorithms take the form of stochastic gradient algorithms and their variants. And if you think about it, this is like a dynamical system, a noisy one in parameter space, right? So there's also a lot of interesting analysis on what you can do to try to understand how this training algorithm behave. So a lot of these new questions really arise from an interplay of compositional or dynamical structures present in machine learning. So if you want to roughly categorize these interactions, here's a rough way to categorize them. The first one is machine learning via dynamical systems. So this is where we use tools from dynamical systems or differential equations control to try to understand certain aspects of deep learning, machine learning or deep learning. So for example, like dynamical formulation of deep learning, continuum limit of residual networks that we heard before, and also dynamical analysis of learning algorithms, right? And of course, numerical analysis and how it corresponds to architecture design. So this is using tools from dynamics to understand machine learning or deep learning. Now, second category interactions is machine learning for dynamical systems. This is where when we are trying to study dynamical systems in a data-driven way, there's often some interactions between what kind of models we use and what kind of dynamical data we deal with. Right? For example, time series forecasting. What is the best way to forecast time series, let's say using recurrent neural networks, and how does the behavior of approximation optimization of this neural network correspond or depend on the structure of the data. So this is where you use machine learning to resolve some problems involving dynamical systems. And the last one is we call it machine learning of dynamical systems. You can think of it as very similar to the second one, except that here the goal is really to learn an underlying dynamical system. Like you want to recover some dynamical system, a representation of it through observational trajectories. Or you want to learn a reduced order model of a particular dynamics you observe, which finds a lot of applications in science and engineering. So today's talk, I'll mostly focus on this first two categories of interactions, and in particular, what kind of mathematical questions may be of interest. So to describe the mathematical question, I will briefly review what supervised learning entails in terms of a mathematical problem. So essentially, supervised learning is about how to make predictions, right? So you have a data set consisting of inputs and outputs, and you have some target function that's unknown to you that maps these inputs to outputs. Okay, in the simplest case, this is just a deterministic function. For example, the inputs can be pictures of cats and dogs, and the outputs will be the labels, cat or dog, or the vectorized representation. And this unknown function f star is the thing that always, in some sense, an oracle that assigns the correct label to each of the inputs. Now, your goal, of course, is to observe enough of this data so that you can learn or approximate this function using information from this data set. Now, how do you approximate the function? The first step is usually defining some hypothesis space. So this hypothesis space is just a set of functions that are convenient to represent on the computer or convenient to describe or understand by us. For example, in the linear models for regression classification, this set of hypothesis space is just a set of linear combinations of some fixed basis functions. Okay, and shallow neural network, you can think of it as some nonlinear generalization of this, is where it's still a linear combination of basis functions, except this basis functions take the form of the familiar, affine transformation followed by nonlinear activation. And what's different really between them is that these basis functions are a priori not fixed. You adapt them to data. So the training parameters also includes the parameters in these basis functions or building blocks, okay? And of course, deep neural network is special in that instead of making some linear combinations of some simple basis functions, it really builds its complexity through composing many of these transformations together. Okay. So once you have a hypothesis space, then there's several questions you can pose in terms of supervised learning. The first one is most basic and is the focus of today's my presentation, is the problem of approximation. It basically asks if we have some target or some class of targets, let's say continuous functions, and we have defined a hypothesis space, then how close is the closest point in the hypothesis space to this target? Okay, perhaps in some limit where the hypothesis space complexity goes to infinity. Now, this error is called the approximation error. Okay, but of course, I want to emphasize this is not the only problem one is interested in, because even if this error is very small, there's still a chance that it's very difficult to find such a good model. For example, starting from initial guess, how can you find a particular best model in this hypothesis space? Now, of course, we do that by learning. So there's this trajectory is some training or optimization algorithm, and you arrive at a learned model. Now, of course, they are different. So how are they different? There's several errors that are interesting. The first one is called the optimization error, because usually we do this training by minimizing some empirical risk. So this is the loss function defining your training samples, right? So after a finite number of iterations, you're not going to get a zero training error. You're always going to get some finite error, and this error is optimization error. But of course, the empirical risk minimizer, which depends on the samples, is not the best possible model because it's a finite number of samples, right? So the difference between this the best model or the population risk or expected risk minimizer and the empirical risk minimizer is called the generalization error. So if you see that your learned model and your target are really separated by a few errors, approximation, generalization, optimization, and many works are studying some or many of this several of these together. And I think it's a very interesting blend of areas in mathematics, because if you think about traditional approximation theory harmonic analysis, usually one is more focused on this part, whereas statistics variously usually focus on the generalization, and of course study optimization algorithms or focus on the optimization error. So this supervised learning kind of nicely combines all three together, and there's a very interesting interactions between them. Okay, but this talk I will mostly focus on the approximation part, and in particular its interaction with this compositional or dynamical structure. And I'll talk about two kinds of problems that is relevant. So the first kind of problem is an approximation theory for continuous time idealization of residual networks. Yeah, and you might have heard that in the earlier talk today as well. So first, I want to state the problem of approximation, or the universal approximation property. Okay, so universal approximation property basically says that it's a property of hypothesis space. It asks whether if you're given a target function f star in some in some concept space or in some set, let's say continuous functions, and an arbitrary error tolerance epsilon that's greater than 0, does there always exist some function in the hypothesis space such that its distance from the target is smaller than epsilon? In other words, if you look at this picture, universal approximation just says that this approximation error distance can be made as small as possible, as you want, as small as you like. Okay, smaller than any positive number. Now, if your hypothesis has that property, then it's called a universal approximation. Now, of course, you can ask this for any hypothesis space, and for many basis sets in linear combination hypothesis space, the study of how fast or how well a hypothesis space can approximate certain functions is very well understood. But here was the new question, in particular in deep learning, is that how can we achieve this universal approximation without doing linear combinations, but doing compositions or dynamics? Okay, and that is in some sense a more novel mathematical question. So the way that we analyze this problem, well, one way we can do it is by the so-called continuum idealization. Okay, so in other words, we look at a deep residual neural network, which is, you can think in general is it's some difference equation that has a residual term here xk, plus this fk just represents the general nonlinear transformation at each layer, the non-residual part plus the residual part. And the idealization is just imagining there's many steps of this, perhaps with some step size multiplied to the front, so that this in some temporal limit, it does become a continuous time dynamical system. Now, of course, you hear from earlier talk that this limit it depends on how you take this limit. Okay, but nevertheless, the viewpoint here is really to regard this as some idealization of the deep neural network that captures some essential properties such as dynamics. And our goal is to analyze in this idealized continuous dynamical systems idealization of the residual network, what can we say about its approximation properties? And of course, this continuum idealization is very commonly used in science and engineering and mathematics. For example, in solids and fluids, they are essentially discrete structures, but we usually take some continuum limit in order to simplify analysis. Okay, so once we take this continuum limit, then we realize that approximating functions through dynamics is really something to do with how the flow rearranges the points. Okay, so what do I mean by that? So here, this is a two-class classification problem. It's different colors, depends on different class. So clearly, this function, this problem is not linearly separable. That means I cannot draw a line that separates these two points. So these two group of points. So what I'm going to do is to feed these points as initial conditions to some ordinary differential equation, which is just a realization of that dynamical system idealization. And we're going to evolve these for a set period of time, and then we can see what happens. Okay, so I'm going to evolve this according to the ODE on the right, and it somehow unfolds the space and rearrange these points so that at the end it becomes a very easy classification problem. You can just draw a vertical line and you classify them. Okay, so of course this is a rather contrived example, but it shows you that how dynamics or composition can help you approximate function is you can think of it as a way to modify the domain progressively through a flow or flow map, so that at the end of that flow, you arrive with a much easier function to approximate. Okay, so this is the basic paradigm of the analysis here. So we really want to ask a very general mathematical question in the following form. So imagine that we have some input x, which is mapped to y by some target function f star. Okay, how can a dynamical system approximate this function? You can think of it as how does a very deep residual net approximate this function? you can think of it as having two parts. The first part is a flow. Okay, so this is your deep residual networks continuum idealization, which takes its initial condition as that point x. Okay, and it feeds into a dynamics for some period of time t to get a final condition xt. So you can think of this as unfolded configuration of the points, and then you apply a very simple function g to the end to arrive at output. Okay, and the goal is, of course, to choose this parameter theta t or choose the function g so that this composite function is very similar to this f star. Okay, so to here, it will be good to define two families of functions. The first family of function, we can call it transformational family. It just means that the family of possible flow maps or transformation maps induced by this dynamical system. So we can write this in an even more a cleaner abstract way, which is we have an ODE x dot t, whose forcing term, or the right hand side, whose vector field is obtained from some set of functions f. Okay, so this f and the final time t basically defines the complexity of this. So this is the group of all transformation maps or flow maps induced by this dynamics. And finally, on the last part, we have a terminal family of functions, which is a family of functions that maps the last layer into the outputs. Okay, and this gives us a compositional hypothesis space of composing these two together, and then we can take the union of all possible times. Okay, so the complexity of this hypothesis space is entirely controlled by f and g. So the mathematical question we want to answer is what conditions on f and g are sufficient to induce the universal approximation property. Okay, so here we don't really assume f and g has anything to do with neural networks. It can be very general dynamical systems, and this is really a question about dynamical systems. So what sufficient conditions are there on this controlled dynamics so that you can represent any function through its flow map? And it turns out we can prove a quite a general, well, sufficiently general sufficient conditions for approximation, which shows that in dimensions greater than 2, you need to verify a few conditions on this on your classes functions f and g. This f you can think of as the complexity of each layer. You only need to satisfy the condition that it is somewhat affine invariant. So this is a weaker version of affine invariance. That means if you take the affine transformation, you're still within that space. And its convolution, its convex hull contains a well function. So what is a well function? The well function is some function like this, where in the convex set it is 0 and everywhere else is non-zero. Okay, so this is a just general is a form of this function. You can think of it as somewhat motivated by the ReLU functions linear combinations. And once the f this layer satisfies these conditions, plus some non-degeneracy condition, which says that the last layer or the last function g must contain something that covers the range of f star. Because when you do composition, you can never expand the range of the function, right? So you need the last part to have sufficient range, which is usually satisfied by any non-degenerate linear functions. So once you have this three properties, then you can prove that a universal approximation is possible. And of course, these you can verify for a lot of neural network architectures. They do satisfy this property, but of course, this property is not limited to neural networks. And you can think of it as something about approximation through dynamics in general. And of course, you can show that in one dimensions, in one dimensions, there's some caveat because there's some topological constraints in one dimension for continuous dynamical systems. So in one dimension, this remains true only if we take increasing functions as a target. Okay. We can also prove some approximation rates in T in the one-dimensional case. That means how long do I need the dynamics to be to approximate the functions of certain complexity. We can give some estimates for dimension 1, but I think in general, in higher dimensions, this characterization is still open. And there's very interesting connections of this problem with controllability. There's some recent works, and I think there's 1 or 2 more that also came up that is not here on using control theory to try to establish some version of this result. Okay, so this is a first on the ResNet, and so I have about 10 minutes. So in the second part, I'll briefly talk about what we can say about a different kind of problems that involves a very interesting interplay of the dynamical structures in the model and the data. And this is regarding recurrent neural networks. So learning dynamical relationships is very important in practice, for example, in price forecasting, machine translation, and for example, learning response systems, like if you give systems some kick, how do you expect some dynamical system to respond, which is very important in engineering. Now, the common feature is that this input-output relationship is essentially dynamics. That means each output doesn't depend on just the input in the current moment. It depends on input in the history as well. Okay, so in other words, we need to model not just one relationship, but a sequence of input relationships, input-output relationships. In other words, the data you get also has some dynamical structure or temporal dependence in it. And we want to investigate what happens if we use a recurrent neural network, which has a dynamical structure of composition in it, to learn this data. And this is an important problem in practice because we observe sometimes the recurrent neural network has poor performance for some problems, but not others. So can we get a mathematical understanding of that? Is the goal of this work. So what is the basic mathematical setting here is that in the static setting, right, we are just looking at a function, a mapping between some vector and another vector, right? So this is just one target function. But in the dynamic setting, we can think of the input and output as both sequences, right? Temporal sequences, or otherwise, general sequences. And our target is not just one, function, but really a sequence of functions that gives each output, and each, output may depend potentially on the entire sequence of inputs. Okay, so the goal of static supervised learning that we discussed before is to approximate a sort of function f star. But dynamic-wise, we're really trying to approximate or learn a sequence of functions or functionals h star, which depends on the entire input sequence. So one very popular network that's used to achieve this purpose is the recurrent neural network. Okay, so this is the usual recurrent network in simplest form of a recurrent neural network, which is we introduce the hidden state h, and then we have a very similar kind of neural network as feed forward, except that at each layer, our W. Hello? At each layer, the weight is the same, and then we also have some dependence on the inputs. Okay, and then our outputs are predicted as some readout of this dynamic, this hidden state hk. Okay, so if you look at the graph. Here, the H hidden state will evolve in time, and the input sequence will be inputs to this dynamics or forcing to this dynamics, and the output will be readout, some linear or nonlinear readout of this state.
Actually, you have about 5 minutes.
Okay, so the RNN parameterizes the sequence of functions together, right? So it's not just one function, and it is really a sequence of functions because each output actually depends on the entire history of the inputs through these hidden states. Okay, and training RNN is just adjusting these parameters so that you have an approximation of this sequence of functionals with some target functionals. Okay, so empirically, it is found that this memory can affect RNN performance. That means if we have data that has long time dependence between the output and the input, then you have some problems with approximation RNN. This is empirical law or fact. But can we understand this from a mathematical point of view? It really requires us to define precisely what is memory. Okay, and it turns out that we can do that. And the idea is to take a continuum approach again, right, to idealize that recurrent neural network as a differential equation. This time, the ways will be time independent, and we're going to take a further simplification by saying that sigma is leading. Okay, and in this case, although we sort of threw away a lot of the details, of nonlinearity in neural network, but it still preserves this dynamical feature, which is the important thing here because we want to talk about memory. And what we can show is that we can show this approximation can be done efficiently if and only if there's some exponential decay in the memory of your target function. Okay, so how? And the rest of the time, I just want to make perhaps use this picture to explain to you what that actually means. So, for example, if we have a input signal, okay, something like this, and then this input signal is changing for the first part, right, and it stops changing at the second part, okay, and this is kind of nice and smooth. Now, there's two possible responses to this. You can think of this as target functionals that maps into the output. So in the first data set or the first target functional, this is the output, and the second one, this is the output. Now, the results that we show is that for this kind of output, RN is, this kind of relationship, RN is very efficient. You can actually approximate this kind of relationship very well using few neurons, whereas the second part is not good. So the key concept is smoothness and memory. So what does smoothness mean? It means that if we have a very smooth input signal, then my output is also smooth. Okay, this is the case on the left, but it's not the case on the right. The second one is that you can see that since the input stopped changing after a while, the output also stopped changing after a while. Okay, that means that it doesn't really depend on very far away, the inputs from far away, or it has exponentially small dependence. Well, as the right-hand side, the story is different, right? It still continues changing erratically. Okay, so it turns out that we can actually make all these concepts precise by just studying what is the response, so what is the output of this target functionals if we give it a temporally constant input. And its smoothness of that mapping will tell us how smooth these functionals are, and its dependence on its past values, right? It's basically its derivatives will tell us how this functional's memory behaves as a function of time. Okay, so the first approximate result we can show is the following. Again, you don't need to process this this result, but I just want to highlight what this says basically is the first condition here. If we assume that these functionals have some exponentially decaying structure, right? That means that if you give it a constant signal, its derivative decays exponentially, the output of the derivative. The derivative of the output. Then we can have an approximation estimate, which is uniform in time, and it decays like some power of number of nodes. Okay, so this rate estimate highlights several things. First of all, like this power alpha depends on the smoothness of your output signal. This is usually what one expects in approximation theory because smooth functions are easier to approximate. But the memory dependence is new. Here, it basically says that if our temporal derivatives of my response to constant signal decays like exponential, then I can have a very good approximation rate. Now, the natural question is, what happens if we don't? Okay, if we don't have this exponential decay, it's very possible that we don't. So hidden in this result is actually a result of cursor memory, which says that if, for example, if your output of a constant signal doesn't decay like an exponential, but say decays like a power law, then as this power goes to zero, you will need an exponentially large number of neurons to be able to achieve approximation to a certain accuracy epsilon. Okay, so this is very much like the Bellman's curse of dimensionality, but except this time is the curse of memory. Is when you have long memory, you need exponentially large number of neurons to approximate. Okay, and in fact, you can make this precise by a converse result, which I will not talk too much about, which says that if you can approximate some functions using functionals using recurrent neural networks uniformly, then that functionals must have some decay structure. Okay, so it's an inverse approximation theorem. And you can, in those of you who are familiar with the approximation theory, will see that the first kind of direct theorem is the Jackson type, and the second type is the Bernstein type. Okay, and the lesson here is really there's a cursor memory approximation, and this is really not about exploding vanishing gradients in optimization, as investigated by very nice papers previously, but this is really about the architecture itself and its approximation properties. So we can also extend this analysis very similar, setting to the convolutional case and obtain some results. So I will not have time to talk about it, but we have some paper this year on how to extend this analysis to really tell the difference between different types of temporal architectures and how they affect approximation properties. Okay, so I'll end here with a quick summary. Is that in the first part we talk about the flow map approximation, which you can think of as using a dynamical Simpsons flow, this flow group on the flow map to approximate functions from X to Y. The second part in recurrent neural network, you can think of it as using a forced dynamical system. So it's a dynamical system of external forcing and readout to approximate a sequence-to-sequence relationship. So this is really two natural ways how you would use a dynamical system to represent functions or functionals. Now, there's many generalizations of the previous results, that some of which we're working on. For example, how do you build in symmetry? Like the graph neural network features into this compositional and dynamical approximation? How do you extend this linear theory to nonlinear cases? And how do you understand more architectures? Okay, so there's many interesting future questions to be answered. So these are some references that are relevant to what I've discussed today, and I'm happy to take some questions.
Yeah, perfect. Thank you so much, Qianxiao, for this excellent talk. A lot of applause in Cambridge, some from here as well. I would first want to make a quick announcement. So I dropped a small message in the chat window. The next 2 hours are reserved, I think, for lunch, at least for the Cambridge people, and poster sessions, which will be held virtually on GatherTown. So there is a link here, which you should have received in your welcome package, and also a password you cannot join. And I really highly recommend. I'm looking forward to joining the session after a quick break, because that's also an opportunity probably to talk with other participants wherever they are at. If you haven't used GatherTown, it's a lot of fun. So I hope to see you there, and hopefully also to see people visit all the posters. So thanks for the poster presenters for that. We are at the time limit, so if there are quick questions for Qianxiao, we can ask him now. If people need to leave, they can leave. There's one question by Franca in the chat window. Can you comment on where assumption 3 around page 11 comes from? Is it related to the ReLU activation function?
Right. Okay. So I think it's this assumption, right? So yeah, this is the key assumption in the result with one sufficient condition. So it is somewhat related, but not quite. So this is a general condition. It says that if you have your control family F, so you remember F is like the set of functions or the forcings, vector fields, you can have it on right-hand side of your equation, right? So we need the convex hull of this, or the closure of the convex hull of these functions to include a type of function like the right-hand side, okay? So this includes you can think of as average of 2 ReLU functions, but of course it's not limited to that. The only thing that we care about for this function is the 2 properties. One, on the convex set, it is 0, okay? And outside of this, the closure of this convex set is non-zero. Okay, so what is the purpose of this function is that this allows us to build very general rearrangement dynamics, because if my point is actually inside this, this well, which is 0, it's not gonna move, right? And if it's outside this well, it's gonna move with certain rate. Now, if we can have some sort of affine invariance, very weak affine invariance, we can try to move this well around or combine them with other of these wells to make sure that we can move points, sufficiently well throughout the entire space. It turns out this is actually sufficient to achieve approximation. Okay, so it is. You can think of it as, it's satisfied by some linear combinations ReLU functions, but of course it includes other functions as well, because we only need the closure of the convex hull to have that function. So almost many architectures you can think of, or even something that doesn't resemble a neural network at all, contains such a function in this convex closure of the convex hull. So this closure is in the usual compact convergence topology.
So I also had a question about that part, Qianxiao. So maybe I'm not understanding the assumption very well, but I know that for certain data sets, the ResNet needs the width of the feature space needs to be increased somehow, which is not the case for your architectures. So for example, if we have a well-posed neural ODE in the end, then say if you have your 2 classes arranged in concentric circles, so a few points in the inside and a few points in the outside, are not really classifiable unless you change the dimensions.
So yeah,
is it reflected?
Yeah, that's a very, very interesting question. So we also see this statement written in some papers as well. Here, basically, I want to make an important distinction, I think, between approximation and representation. So it is true that a continuous time dynamical system always gives you a homomorphic map, right? The flow map is a continuous, bicontinuous, map, right? Invertible, bicontinuous. So of course, this map cannot represent any map that doesn't have that regularity property. And all those examples are precisely those maps that cannot have that such regularity property. But it does not preclude the fact that this is actually dense in a bigger space, because we only need to approximate it in some LP sense, let's say. So here we just need to show that these homomorphic functions, right, or these homomorphisms can actually approximate the functions that are not bicontinuous. And in this case, this is actually known. There is some previous work using, optimal transport theory, and in particular this polar factorization, to prove that these homomorphisms indeed can be dense in the space of a bigger space or a weaker structure. So those counterexamples really on representation. They do not say anything about approximation.
Okay, yeah, got it. That makes a lot of sense. I mean,
yeah.
Thanks for clarifying that. So I would really, as a chair, try to conclude the morning session now. It's tempting and probably very good to keep on quizzing Qianxiao with more questions. But if people need to leave, then that's fine. And yeah, let's thank all the speakers again for the morning session, and see everyone at the posters, which hopefully is also an opportunity to chat more with any of the speakers from the morning session or any of the other participants.
Please, before all of you are leaving for lunch, we're going to have a quick picture outside.
Okay, yeah, always follow Carola's advice there. So only for the Cambridge people, right?
Thank you, Lars. Thank you.
Everyone.
Yeah, so thanks, Rama, Yuguan, thanks for the excellent talk.
Thank you.
Qianxiao, like for these examples, like that are not reflected by diffeomorphism, what we realize in training, you really have a hard time because
I agree. So this is only approximation property, as I emphasized before. It doesn't tell you that this is easier to learn. And it will be very interesting to study the training dynamics and how it pertains. I think in general, like one very important question is what kind of functions are easy to learn using compositional or dynamical structures. And we have some piece of evidence here and there, but I think it lacks a comprehensive theory, both on the approximation side. Like we can characterize some approximation rates in very simple systems, but in high dimensions and in general, what is the right complexity measure that reflects what functions are easy to approximate using dynamics is not clear.
Well,
and the second part is
what's the definition of easy?
I mean, maybe some sort of well understood, right? So you can describe the regularity, like our typical notions of regularity, like smoothness, right? They really are, really related to linear combinations of nice functions. And that's, these traditional Fourier analysis tells us that, but we don't really have a good intuition of what functions are very easy to approximate under dynamics or composition. We don't have this equivalent notion of regularity as far as I can see for those kind of systems. And that's only on the approximation side. On the optimization side, it's a very difficult and interesting problem. In fact, the second part of my talk, I didn't have time to go through, but we also discussed some optimization properties of recurrent neural networks, which even in the very simple cases, you can show that it's extremely non-trivial. And it also depends on the memory of your input data. So we can make that precise for simple examples, but there's still lots of work to do.
So what's then the opinion on like long-term, short-term memory architectures and other things, like are those less affected by the memory, or is there no free lunch here?
My feeling is that they're definitely doing something to alleviate the memory issue, but I think what's not clear, at least to me right now, is whether that comes from the fact that it's easier to train by letting gradients flow nicely, or is it because fundamentally the architecture is more expressive for long-term memory? Now you cannot tell that from an experiment by itself, right? Because you don't. I meat, at least it's not easy to tell from an experiment.
It's impossible because also what you realize that for two different data sets, the conclusions would be very different.
Yeah. So it definitely depends on the structure of data. It's a lesson we learn. So like the approximation, at least both approximation and optimization, whether these things do well really depends on what kind of structures that's present in your data, which is also dynamical. And in some sense, they have to be compatible. So the second part, like this paper I didn't talk about, which is the CNN paper, shows that like temporal sequences can have different structures, like this one. This is based on this Google WaveNet, and basically using convolutions to learn time series. And you realize that these networks are adapted to a different kind of structure in the data. So if the structure is present, then you should use this kind of networks. If it's not present and another structure is present, then you use another kind of network. and that's is an interesting question. We're starting to try to understand.
Yeah, really nice, really nice. Okay, great seeing you. I'll take a quick break now and then go to the poster session.
Yeah, nice seeing you, and thanks to you all.
Thanks for the awesome talk. Okay, see you later.
See you.